Okay, so Euler's method is a numerical method for looking at differential equations, which means it's not exact. It's close, but not exact. So we can define that error over a fixed interval as being the exact value minus the approximate value. And if we use n steps over that fixed interval, then the error is approximately proportional to 1 over n. Okay, so not the best error margin, but I think that this gives you a good idea of what a numerical method looks like for differential equations. Okay, so just like with our left and right Riemann sums, we had more accurate ways of doing those sums, right? Like we have the trapezoid rule and Simpson's rule. There are much more accurate numerical integration techniques, okay, like Runge-Kutta, finite element method, things like that, that you would look at in a more advanced course. Okay, but I wanted to give you a taste of what that numerical method might look like. And Euler's is a great method to start with. Okay, so as far as this number of steps goes, in this picture here, this black curve is the exact solution. And here we have 4 approximations made using Euler's method, but they each have a different step size. So the largest step size is this red line, and the smallest step size is this blue line here. Okay, so the smaller your step size is, okay, that means the more number of steps that are going to be used over this fixed interval, and then the error is going to be a lot smaller. Okay, so generally with numerical methods, we don't do these by hand with a calculator. They're generally programmed into a computer. Okay, for the reason that the smaller that step size, the closer we are to the actual solution curve, and the better our approximation will be if we're using a smaller and smaller step size. So we use a computer to speed that work up for us. And even if you chose a super, super, super tiny step size, a computer would be able to plow through that really quickly. The worst thing that might happen is it takes a slightly longer runtime depending on how involved your system of differential equations are. But a computer is definitely the way to go in terms of numerical integration techniques. All right, so let's look at this example from the previous page. Dy dx is equal to x plus 5, and our initial condition is that y of 0 is equal to 1. Okay, and I have a variety of different step sizes here, all the way from 0.5 to 0.001. And what we've done is we've used Euler's method to approximate y of 0.5 and y of 1 using these step sizes. And remember that this y of 0.5, this is an approximation for a value on our solution curve. Okay. So as our step size decreased, you notice these get smaller, what happens with our Euler estimate is that it's going to approach the true value. So that true value of y of 0.5 or y of 1. Okay, so instead of having an estimation of y of 0.5 being 1.5, what we're doing is we're finding that really that true value is going to be around 1.79 something. Okay. All right, and then one thing to note is that the error compounds. So the larger the step size, that faster that error is going to start to add up. Okay, and especially as you start to travel these bigger distances, right, so you're getting further away from your initial condition, and so as you march out over time, you'll notice this isn't too big of a difference here. This is about 0.3, but the difference that we get out here to y of 1, we're going from 2.5 to 3.4, so that's a difference of 0.9. That's quite bigger difference between the estimate and the true value. Now, some of these estimates in here are a whole lot better. And so you have to weigh those things when you are looking at using a numerical method. You want a good step size that will get you pretty close to the true solution, but you don't want it to be such a small step size that you're going to be running this computer over and over forever and ever waiting for it to come up with an answer. Okay, so there is a happy medium there and a happy balance. And of course, the differential equations will really address that for you.